While identification of patterns and relationships is critical in data analysis, this task is particularly challenging with high-dimensional data. Dimensionality reduction techniques utilized in visual analytics partially mitigate these challenges, but with often limited features for an exploratory, interactive approach. In this work, we present DimLift, a novel visual analytics method that lifts interesting relationships to the surface through the creation and navigation of dimensional bundles. Here, we define dimensional bundles as groups of dimensions that contribute similarly to the overall variance of a dataset. We form dimensional bundles through a combination of iterative dimensionality reduction and user interaction techniques. We demonstrate our pipeline with a synthetic 10-dimensional dataset. Bundles are initially created algorithmically using factor analysis of mixed data, or FAMD. While a standard approach, shown here on the left, applies the method only once and produces several principal components that each contain all 10 dimensions at broadly varying contributions, our iterative approach, in contrast, extracts and bundles dimensions meeting a contribution threshold in the first principal component of each iteration from the main pool of dimensions, as shown here. These extracted dimensions are the inputs to a given dimensional bundle. We rerun the FAMD algorithm on these extracted dimensions to create the bundle components, where we keep the first and second principal components to describe the overall variance, in addition to the raw contributing dimensions, shown here. We continue iterating and extracting contributing dimensions from the main pool until the contributing variance for the possible bundle falls below the variance contributed by any of the dimensions alone. These dimensions then remain unbundled, shown here. Our visual aggregation to a multi-level parallel coordinates plot and accompanying dimension scatter plot allows users to explore the data through numerous interactions. Panning allows the user to focus attention on a subset of bundles. A context donut chart glyph shows the bundles in purple and unbundled dimensions in gray. Hovering over each axis provides information on the goodness of the grouping, missingness, and bundle composition. Brushing over a bundle axis creates adjustable subsets on the axes or in the adjacent panel. Subset bundles show in darker purple in the donut chart. Swapping the bundle axis from its first to second principal component shows the differing contributions to the variance within a bundle and allows correlation assessment from a more subtle perspective. Drilling down to a plot of first versus second principal component item scores shows item spread or clustering within a bundle. Drilling further down to the contributing bundle dimensions allows assessment of correlations within a bundle, which can also be compared outside the bundle. Structural interactions allow the user to recompose dimensional bundles. These can be created from scratch based on interesting clusters by descriptive statistics in the dimension overview scatterplot or by searching directly. After running the FAMD on the selected set, the new bundle is created in the parallel coordinates plot. Existing bundles may also be modified by adding or removing dimensions in the dimensionality reduction panel. Following FAMD, the updated variance contributions and correlations can be viewed in the parallel coordinates plot. We now briefly demonstrate DimLift for use in exploratory hypothesis generation in a clinical cohort dataset for cerebral small vessel disease, or CSVD, which was part of a 2-expert case study, including our clinical collaborator and fellow co-author of this work. On an initial overview, experts discovered 2 notably interesting bundles generated. One bundle included lacunas and microbleeds together, and another included nicotine, intracerebral hemorrhage, and enlarged perivascular spaces. Undetectable in their standard analysis approach, this generates new hypotheses on the correlation of these respective dimensions for deeper analysis. On a closer inspection of a bundle containing primarily imaging data, experts could drill into this bundle to note 2 distinctive clusters in the principal component plot. Experts further note in Principal Component 2 that Boston's Strive criteria has been lifted to the surface as one of the more influential dimensions in this group, which is interesting since this is a known biomarker for CSVD. Experts add APOE, another known biomarker, to this bundle. Swapping the axes allows for rapid subset selection of the top group. Subsequent exploration of correlations within this bundle shows non-imputed items for Boston's drive criteria, sex, and group, a consistent range for white matter and CSF volume values, and consistent APOE values that merit further investigation. By creating dimensional bundles through an iterative and algorithmic user-driven process, the DimLift method provides a novel means to discover subtle patterns in relationships and high-dimensional data by lifting them to the surface.